Continuing on 5.1, we're going to try to make these separable differential equations before we try to solve it. Because right now they're not separable. So this, come on. All right, that doesn't look very clear. Let's clear that up. All right. So we can use properties of exponents here to rewrite this as e to the x over e to the y. Now if we do that, we can separate it. We can make it e to the y dy equals e to the x dx. And we can integrate that. E to the x is such a nice one. That would be e to the y equals e to the x plus c. All right. So now we are just trying to find a general solution, y equals f of x. So we can take the ln of both sides, and we would get y equals ln of e to the x plus c. And that's our answer. That's it. So what can we do with this next one? Well, let's try moving some things around. If dy dx, let's move the x to the other side. X plus xy squared. Can we separate it? Not yet. Let's see what we can do. We can factor. We can make that 1 plus y squared. Now I have x's and y's separate. So I can write this as 1 over 1 plus y squared. Oh, I forgot the dy. Okay. Equals x dx. Now that I've separated the variables, I can go ahead and integrate. So this one, hopefully you remember, that's arctan, or inverse tangent. And this would be 1/2 x squared plus c. One more step, solve for y. Y equals tangent of that. To solve for y, we would just have to take the tangent of both sides. There we go. Now, if they gave us an initial condition, we could find a particular solution, but we don't have to, so we're not. All right, now this one, we need to find a general solution. Now remember, before we can even try to get a solution, we need to separate the variables. Aha, so I can do that. Now we can integrate. 1/2 y squared equals 1/2 x squared plus c. Multiply both sides by 2. Remember, 2c is still just c. And then the general solution for this would be y equals plus or minus the square root of the quantity x squared plus c. Now we're going to look at 4 particular solutions for this. All right. So for part A, if it's going to pass through the point 0, 4, that would mean y is 4 and x is 0. All right, so we can't have positive or negative. We're just going to disregard the negative because it's 4. It's positive 4. So we can just know we have to have the positive root. And the square root of c equals 4. So c equals 16. That means our particular solution is going to be y equals positive x squared plus 16. Okay, let's do B. At 0, negative 4, we would have negative 4 equals, so we're going to have negative square root of x, 0 squared plus c. So the negatives will be there. We know that the answer is going to have to be negative square root of something. And in this case, if we multiply by negative 1 and square it, we're going to get 16 equals c again. So we'll get negative x squared plus 16. Okay, for part C, let's try a different color. So at the point negative 4, 0, we have 0 equals 16 plus c, because when you square negative 4, you get 16. So if we square both sides, we get this. And so c is negative 16. So y equals positive x squared minus 16. And lastly, we have 0, 0. So at 0, 0, we'd get 0 equals square root of 0 plus c. So c equals 0. Y would be the square root of x squared plus 0, but the square root of x squared, a lot of you are going to say that's x. It's not absolute value of x. How exciting! All right, so on to laws of exponential change. Some of these problems we can do part of it using methods that we learned in pre-calculus, but we're going to try to stick to the calculus method. Now we have this really important mathematical idea. If the rate of change is directly proportional to a quantity itself, then that's going to give us a really nice equation to work with. All right, and we're going to see what that equation is as we solve this. So we're going to solve this by separating the variables. So we notice we don't have a t as a variable, but we do have a k, which is a constant. So we're going to move that y over to put that with dy, and then we have k dt. We're going to go ahead and integrate both sides. Now remember, 1 over y, the antiderivative of that is ln of absolute value of y, and then we would have kt plus c. Solving for y, okay, if we exponentiate both sides, we get y equals, technically absolute value of y, equals e to the kt plus c. All right, we can separate that into two conditions, or we can remember that we can get rid of the absolute value symbol by putting a big old C in the front. All right, so if we have this, the rate of change is directly proportional to that quantity itself, we can use this equation to help us figure out the problem. It's a really big idea, so big that it's in a box and it says memorize it. All right, find the value of k. Since we know it's directly, let's see, directly proportional, it says this, all right? We know that the equation's going to be in this form. So let's see, we know that this is 1600, the population, it started at 400, and it took 3 hours. All right, so solving for k, let's see, ln 4 equals 3k. So k would be ln 4 divided by 3. Now, that's very helpful for this next question. It says, how fast does the population change it? Because we know dp dt equals k times p, k is this, population is 3,000. So how fast is it changing? It would be 1,000 times ln of 4, whatever that is, and the population, we could say bacteria per hour, because it's talking about a rate. Great. All right, let's try another one like that. We have this directly proportional idea, so we know our equation is going to be in this form. Now we're looking at this, our amount is going to triple every 11 hours. So if we started with 1, if we're tripling, we'd end up with 3. And we said every 11 hours. So that makes an equation that's easy to solve. And so ln 3 over over 11 is equal to k. We have defined the value of k. So that's the exact value. And I think if I typed it on the calculator right, that would be the approximation. All right, so we could probably do one more. We're talking about radium, and a lot of times you'll see this with half-life of elements. And so we have radium-226. Okay, I actually just read a book recently called The Radium Girls. It's a pretty good book if you have, you know, in all your spare time. That's a good book to read, and a lot of it takes place in New Jersey, actually. Okay, so we are talking about radium, We're working with equations of this type. All right. So we have an initial mass of 100 milligrams. Okay. Um, and so it has a half-life. That means half of it will be remaining after 1,590 years. It's a long time. So if we take ln of both sides, okay, and then, so that means k equals ln 1/2 divided by 1590. We can actually clean this up, so I'm going to show you one form of the equation. 100, it's going to look a little messy, e to the ln of 1/2 over 1590 t. That says 90 up there. Okay, sure. Or, if you remember from pre-calc, it has a half-life. So that means and using properties of logs and e's, exponential equations, we can change this to 1/2. And then that would be t over 1590. Oops. All right, so now we're going to use this equation, m of t. I'm going to write it a little clearer here. We started with 100. It has a half-life every 1590 years. How much of the original sample remains after 100 years? So we plug 100 into our equation. Oh, what am I doing? Got kind of crazy with the equation, or with the parentheses there. 100 over 1590. And that would be years. I don't have my calculator handy, so that's good enough. Oh, that's not years, is it? We're talking amount. It was in milligrams, I guess. And then the last part of this, how many years, an exact answer, will it take for the sample to have only 3 milligrams remaining? So you can take an estimate of that. It's going to be a while, since it takes 1,500 years for it to divide in half. So I'm not going to give you an approximation because, again, I don't have my calculator handy. But we're trying to see how long it will take for it to have 3 milligrams remaining. So we're going to divide by 100. We need to get that out of the exponent so we can ln both sides. And then we would have t over 1590 times the ln of 1/2. Okay, so I'm going to do two things at once. I'm going to multiply by 1590, and I'm going to divide by ln of 1/2. And that's our time, exactly in years. Now we could have some fun with this. I know that you might not think it's fun, but keep in mind that on a multiple choice part of a test or the AP exam, this top part, you could write this as a whole bunch of different things. Using your properties of logs, it could be something like this, okay, over ln of 1 minus ln of 2, and then what is the ln of 1? Okay, 0, so you could just not have that, and then it would be negative ln of 2. It might be expanded a little bit, maybe the negatives in the top. So just keep in mind that with logs, you have a lot of variety of forms that you could put these things into.